Motion of a charged particle in a uniform electric field. We know that in the case of a point charge, for example, positive, at any point in the space, we have an electric field created by this charge. For example, at this point A, we have, let's take a line. At this point, we have EA. EA. The magnitude of EA. Let's take this one in the X direction. So EA equal K Q divided by R1 square. R1 is the distance from here to here. And on the same line, we take a point B at a distance equal RB. Here it's RA, we can say A, and here we have B. Okay, A in the direction of I. At the point B, EB is equal to KQ divided by RB square in I direction, and so on. We can say C at a distance RC, EC equal KQ divided by RC square. You know that the field is inversely proportional to the distance. So when the distance increases, R increases, the field will decrease. Okay? When the distance decreases, the field increases. Okay, so the field created by a point charge is not constant. We can say it's not uniform electric field because this field will change with respect to the distance. Okay, how can we create a uniform electric field? Let's take two plates. This one we can take like this, and we have a positive. Let's take like this. The negative one, here we have the negative charged object. This plate is negatively charged, and this one positively charged. The field created between these two plates, you know, the positive will create a field will be directed outward of the object. and the negative will create a field. This field will be directed inward to the object. So the field will be out from the positive charge and in to the negative charge, like this. Okay, we can say here we have E field between these two plates. In this case, because this one has minus Q charge and this one has plus Q charge, the field between these two plates is constant. E is constant. You can say also is uniform. It's a uniform electric field. It's a uniform electric field. Now we take, for example, a positive charge injected in this direction with a velocity v. Let's remind you an example. If we have a positive charge with a field at the point P, E, here we have a field like this. If we put a charge at this point, we can say here we have Q1 and here we have Q2. We get a force F equal electric force Fe equal Q2 times the field. Okay, Q1 will create E1 and the force created equal Q2 times E. Okay, each time you have a field and you put a charge in this field, you will get a new electric force. We come back to our case. This positive charge is injected inside the field. So the charge will be in the field. As this charge is positively charged inside the field, we will have electric force Fe. So Fe created on this charge equal Q times the located field E, which is constant. If Q is positive, so Fe and E have same direction. Okay, so this object or the force applied must be directed in the same direction with E because Q is positive. In this case, the object will do a deviation upward because the force applied on the object up. Up. You can do F with this color, like this. Okay? F must be up. So you have a deviation like this. Now we take the case where Q is negative. Q is negative. If Q is negative, initially with a velocity v, inside the field, this negative charge Q will create electric force Fe equal Q times E. Q is negative, so Fe and E have opposite direction. In this case, because the opposite direction, the created electric force must be opposite. Down. This one is F electric. Okay? In this case, the deviation will be directed like this. At any point, you have F down, 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 down. Okay? Now, you know that the field is uniform, so the acceleration is constant, because F will be constant. You know F equal ma by Newton's law. E is constant by this equation. If E is constant, Q is constant, so Fe is constant. If F is constant, so the acceleration must be constant. Second, as we have A is constant, we can use in this case the kinematics equations. You know, x final minus x initial equal half ax t square plus v initial x t, and v final at any point x direction minus v initial x equal ax t. And also if you calculate t from this equation and you substitute its value here, you get v x final square minus v initial x square equal to ax x final minus x initial. It's the same for y. You can put y in the place instead of x. So if here we have the initial position x and y, you can say here the initial position x initial and y initial. And here at this point you have the final position in this example. You have x equal uh, this value. Here you have x. You can choose. Here you have x, and this one is y in the negative direction. Okay, anyway, you can use this kinematics equation to calculate ax, x, vx, vy, and any parameter. Okay, in the application we will understand well how can we calculate each value. Thank you.